All right, so let's kind of talk about spring forces. So spring force follows a specific law. It's called Hooke's law. And Hooke's law states that the force elastic or the spring force should be equal to negative kx. K is a new value for us. K is called the spring constant, which is also just think of it as the stiffness. So if a spring is really stretchy, that's a low K value, a low spring constant. But if a spring is really stiff, then that would give it a high spring constant value, which would require more spring force. And then that X, which actually really we should think about it as delta X, the change in X is the depression or stretch of the spring. So if you, whatever you change the spring by, that distance, that's going to be delta X. Also, Hooke's law is negative, and there is a reason for that. Hooke's law is negative because the spring always acts opposite of the force applied to it. So in this example, they are pulling the spring to the right. And so they're pulling to the right, but that spring, the spring is going to be acting to the left. And that's why Hooke's law is negative. It's just proving that whatever you do to a spring, the spring is going to do the opposite back to you. But I have seen some texts where Hooke's constant is actually an absolute value of K delta X. And that's honestly better for my brain. You can use either one. But with the absolute value, all you have to do is look at a free body diagram to know if it's negative or positive, and you don't need to worry about making Hooke's law negative. Um, I just find that if I use this version of the formula with the negative, I tend to mess it up. The delta X, you need to think about whether that would be positive or negative, and that will change the answer. But if you just take the absolute value and then you look at a free body diagram, okay, if I pull right, the spring is going to pull left, and that would mean that the spring has a negative value, then you don't need to worry about Hooke's law being negative. And I just think that's a lot easier. So either way, you can either use the negative or you can take the absolute value and just refer to a free body diagram to decide if you have a negative or positive spring force. Okay, let's try a simple example. It says a 20 centimeter long spring with a spring constant of 100 newtons per meter, so spring constant is that K value, is stretched to a length of 21 centimeters. What force, so we're looking for the spring force, is required to hold it into that stretch position? Okay, so if we start at 20 centimeters long and then we only move to 21 centimeters, think about what the delta X would be. The change in X is not going to be 21 centimeters. It's going to be the original length and the final length, that distance between it. So really I need to do 21 minus 20, or actually even better, since my spring constant is in meters, I should really actually do 0.21 minus 0.20, which mean the spring only compressed by 0.01 meters. Okay, so now that I know that, the spring force is going to be equal to K delta X. My K is 100 and the change in X is 0.01. And so that would actually give me a value of 1 Newton. Okay, so there's a simple example. This example was really to point out that you have to be careful about the way the distance is worded. So for this problem, 20 centimeters was the starting position and we stretched it to 21. And so that actually made the delta X just 0.01 meters, or 1 centimeter. Okay, so be careful with that. A spring with a spring constant of K and a length of L when hung vertically has a length of L when hung vertically. How far will it stretch if mass M is hung on the end? Okay, so the original length is L. It's asking how far would it stretch at the end. And the rest of it is all just the variables. So we just need to set up an equation. We don't have numbers to solve. But looking at the free body diagram, it looks like the driving force of the system is the force of gravity, and the spring force should be equal but opposite to that. Okay, so if I set up a net force equation, we should not be accelerating, so it should be 0. The spring force is positive since it's up, and the gravity is negative since it's down. Remember, spring force is K delta X, and force of gravity is mg. And I'm pretty much done, but since it gave me that the original length was L, and it asked how far will it stretch to, I don't actually want delta X. I really need to replace delta X with final minus initial, which we're just going to call the final position X. But the original position, it said L, like a length of L. So I'm going to replace delta X with X minus L. And it does want me to solve for X, so I'm going to go ahead and rearrange. First thing I need to do is move mg to the other side. And then work your way inward. So let's go ahead and get rid of that k. K is being multiplied by x minus L. So next step would be take mg and divide it by k. And then if I want x by itself, the last thing to do would be to add L to the other side. And that should be my final answer. Okay, it looks like the next example is actually the same scenario, but it gave me numbers this time. And so I can actually just use the formula I just found and go ahead and plug in actual numbers. So let's find the mass. So the mass is 3 times 9.8. The spring constant for this spring is 75 newtons per meter. And the original length is 20 centimeters, which I do need to change to meters. So I would want to use 0.2. Okay, so let's figure out what final position it should be on. So it looks like this spring should end on 0.59 meters or 59 centimeters. It says repeat it if a 6 kilogram mass were hung. So if a 6 kilogram mass were hung, the only thing that would change is that 3. Everything else should stay the same. So let's see how that's affected. And we got a value of 0.98 meters, which does make sense. We're stretching with we have a double the mass and we pretty much have double the stretch. So that does logically check out. It says, why is the location where the mass naturally hangs called the equilibrium? So equilibrium means that everything should be balanced. And if everything's balanced, we should add up to 0. So it's where the spring is not being stretched or compressed, or if there is a hanging mass on it, it's that point where the force of gravity pulling it down is equal to the spring force. That way the overall net force is 0. And the overall acceleration would also be 0. Okay, so for equilibrium, I guess the key word would be think about balance of forces. Okay, so we have a spring attached to the wall, and then there's a block on the right end. It says the spring constant K is 175 newtons per meter. The block is moved leftwards, and the spring's right end is displaced from 0.35 meters from the wall to 0.225 meters, where it is held in place. So there should be no acceleration. So this time we are pushing it to the left, which does mean that our spring force should be to the right. So we should have a positive spring force. And then all it wants to know is what is the spring force? So we don't even really need to do a free body diagram. We just need to think about K delta X, and it gave me all that information. So K is 175. The change in X, we started at 0.35 and we went to 0.225. So remember, change is final minus initial. And from our free body diagram, we know that that answer should be positive. Okay, so 175. Okay, so when I type that in my calculator, I did get a negative answer, but we're taking the absolute value and just refer to your free body diagram. So my free body diagram points it to the right, and so I'm just going to say that that definitely should be positive. So just refer to the free body diagram to think about whether you want to keep the negative or make it positive. Okay, so that's it for springs. Springs are pretty simple. You just need to remember Hooke's law, and it is on your formula chart. It's K delta X. K is the spring constant, and delta X is that change in position. You can do the negative on Hooke's law, but you'll just have to keep track of whether delta X is negative or positive. But my favorite is to do the absolute value, so there's no worry about if it's negative or positive, and just refer to the free body diagram at the end, and then decide if you want to make your answer negative or positive, depending on if it's going right or left or up or down. Okay, so that's it for springs.